Hi guys, and welcome to another one of the HSC videos on production materials, and now we're into the radioactive section of this topic. So today I want to actually look at nuclear decay and just understanding the different types of radioactive particles and I guess some of the characteristics of them. So three types of radiation, and they are alpha particles, beta particles, and gamma radiation or gamma rays. Each of these is characterized by, I guess, something that makes it easier for us to identify them. So an alpha particle is a positively charged helium isotope. That is, it's a helium nucleus. The alpha particle has 2 protons and 2 neutrons and no electrons. So it's charged, a charge of +2, and it has mass. The beta particle is just a high-speed electron. So a beta particle has no mass, but it has a charge of -1. And I've put those upside down, so let's try again. A charge of -1 and no mass. The gamma is just radiation, so it has no mass and no charge. And the different types of nature of each of these particles can be used to help explain some of their characteristics. So firstly, let's have a look at alpha decay. So alpha decay is common to large atoms because the removal of an alpha particle is removal of mass. So in alpha decay, we're removing mass from our nucleus. So an atom decays into a new atom and emits an alpha particle, which means it's basically giving out 2 protons and 2 neutrons in the form of a helium nucleus, which is the equivalent of an alpha particle. So this is going to drop its atomic number by 2, and it's going to drop its atomic mass by 4. So the unstable nucleus is going to undergo alpha decay as it produces a new nucleus, and of course, since we're changing the number of protons, we're going to actually have a different element here altogether. And then you can see that the alpha particle is made up of both protons and neutrons, and 2 of each. The important thing is that we talk about the helium nucleus to help us understand the nature of an alpha particle. Okay, it's not actually helium, but it does have something that's very, very similar, and that's why sometimes you'll actually see it listed as the 4,2 helium. Just try and be aware of that. This is a title for convenience. We're not trying to say this is a helium atom that's actually being removed here from the nucleus. It's only a combination of 2 protons and 2 neutrons. So for beta decay then, when we look at beta decay, we have, generally speaking, what goes on in beta decay is we have a neutron which has no protons, no charge, but a mass of 1, and it decays into a proton and an electron, which is the beta particle. And as a consequence of this, the number changes, so we turn a neutron into a proton, and the high-speed beta particle actually leaves the nucleus, and it leaves the atom altogether, in fact. So this sort of decay often happens when you have a higher than usual neutron to proton ratio. So we can try and balance up that imbalance of neutrons to protons by turning one of the neutrons into a proton and releasing that high-speed beta particle. So here again, the unstable nucleus, which produces a new nucleus, and because we've got a change in the number of protons, again, we've got a change in the actual element itself, and the high-speed electron, which is the beta particle. Now, the nature of this, I've just kind of explained to you in oversimplified terms here. The excess neutron in the nucleus becomes a proton, and that high-speed electron actually has too much energy to remain in the nucleus, and it leaves. You may, particularly if you do physics, you may have also heard of neutrinos or other subatomic components of the atom, which we won't look at in too much detail in this part of the course. But obviously, if you know more about that and you can include those in your answers, then that's perfectly reasonable. But at this point in time, as long as we're aware that beta decay basically involves the conversion of a neutron into a proton and that high-speed electron, which is our beta particle. And this is basically just a consequence, as I said, of the fact that the nucleus, generally speaking, will have too many neutrons to protons. So we reduce the number of neutrons by 1, we increase the number of protons by 1, and hence we get a change in the stability of that nucleus. Now, it's possible that we can also have an antiparticle here. Just as the high-speed beta particle, we've said, is equivalent to a high-speed electron, you can actually have a beta positive kind of decay. This beta positive is known as a positron, and it too can be released in the process of nuclear breakdown. But it's not actually specified in our syllabus that we need to look at positron decay. So if you're interested, have a look, but it's not something that we need to worry about. The third type of decay is gamma decay, and this is a different type of decay again. Gamma is one of the highest frequency forms of electromagnetic radiation. It has no mass and it has no charge. And so those are going to be important qualities when we look at some of the other properties of particles later on. But it is very high energy. So high frequency, extremely short wavelength, and sometimes alpha and beta decay may also be accompanied by the release of gamma rays. So here we have an unstable nucleus which is producing a new nucleus which may release something like an alpha particle and may also be accompanied by some gamma radiation. Now, the release of gamma radiation itself is not associated with a change in the actual nature of the nucleus itself because it has no charge and no mass. But if it accompanies something like an alpha decay, then obviously there will be a change in the nucleus. Gamma decay is quite different to alpha and beta decay, and that's because gamma is a ray of electromagnetic radiation. It's not a particle. It has no mass, and it has no charge. And as a consequence of that, we get a large amount of energy released from the nucleus of the atom. So it actually leaves the nucleus at a lower energy level than what it was prior to the release of the gamma ray. So the main consequence is lowering in the energy level, but no change in its actual nuclear composition. So the number of protons stays the same, and the number of neutrons also stays the same. So there's two important things to talk about. I guess there's a third, which is half-life, but we'll go into that a little bit later on. But when we're specifically referring to these three different types of radiation, then we want to try and, I guess, focus in on two very important properties. And this is also going to be important when you're looking at the different uses of radioisotopes in industry and medicine. And that is their ability to convert another atom into an ion, which we call the ionizing power. How readily do these particles of radiation cause ionization in other atoms? And the other thing that's very important for us to look at is how far can each of these particles or rays travel through different substances? And we call that their penetrating power. So if we look first at ionizing ability we said was the ability of a particular type of radiation to ionize an atom. So effectively, what that's going to do is it's going to take the atom and punch out an electron in order to turn it into an ion. The ionizing power of radiation is related to the amount of energy that it has. More mass generally means more energy, so heavier forms of radiation are more ionizing. So that means the alpha, which is the most massive, and that would be greater than the beta, and then that would be greater than the gamma, which has no mass at all. So when radiation collides with atoms or molecules, it can change their structure, and the way that it does that is to basically, like billiard or pool balls, knock the electrons out from the atom. And once it does that, when an atom loses an electron, it becomes an ion, and hence we call this ionizing radiation. So if we have a look at this, an alpha particle passing through a stream of other particles, what can happen is that that alpha particle can actually strike, or at least come close enough to one of those atoms in order to drive an electron away, and when it does that, it produces an ion, which is what's left behind. The second important property we need to look at is penetrating power. And penetrating power is how far the different type of radiation will travel through different materials. In this case, penetrating power is linked to size. And the smaller it is, the less it will interact with matter, and therefore the more matter that it can travel through before being stopped. What this means is that in this case, the gamma particle can actually penetrate much further through substances than the beta particle, and this again will penetrate further distances than the alpha particle. So virtually the reverse of ionizing power that we looked at in the last slide. So you can see here in the little animated graphic that the paper actually stops the alpha particle. We put aluminium down a little bit further. The beta particle can travel a little bit further through the air but can't pass through the aluminium. But if we want to store things that are gamma emitters, then we need to make sure that they are very heavily lead lined. This is a fairly important table, and it's worth you taking note of. Put it in your notes, take a copy. This is an easy way of reproducing all of this information if you're required to do so. So we get the three types of radiation: alpha, beta, and gamma. Write those down. They're all Greek letters, which I'm sure you would be aware of by now. The nature of each, so the alpha looks like a helium nucleus with 2 protons and 2 neutrons. The beta particle is a high-speed electron, and the gamma ray is a ray of electromagnetic radiation. Because of the 2 protons, the alpha particle has a 2+ charge, the beta particle has a -1 charge, similar to an electron, and the gamma has no charge at all. Relative masses, equivalent to a mass of 4 for the alpha, same as the mass of an electron for the beta, and nothing for the gamma. And then in terms of ionizing ability, very high for the alpha, moderate for the beta, and low for the gamma. And in terms of penetrating power, exactly the opposite. Low penetration for alpha, moderate penetration for the beta, and very high for the gamma. We can identify charged particles because of the way they interact in electric fields, and so when we fire different alpha, beta, and gamma emitters and allow those particles to pass through electric fields, we can see how they are deflected in those fields to get a sense of the actual charge. When we do that, we notice that the alpha particle, being positive, gets attracted to the negative plate. The beta particle is negative and it gets attracted to the positive plate. But because it's a lighter particle, the force that's acting causes a greater acceleration and a greater change in its velocity, so it bends more, and the gamma won't be attracted to either. It'll just pass straight through the center of the field. So here's a question, a few years back, this one. but a nice flow chart that you get quite often. So from this flow chart, can you use examples to describe the processes by which an unstable isotope undergoes radioactive decay? This particular flow chart shows the sequence of products released during the decay of uranium. And this particular question was worth 3 marks. So when we're answering this question, we need to have a look at what's happening at each step. So the first step causes a drop in the atomic number and a drop in mass. So this must be an alpha particle being released here, 2 and 4. Where we have a horizontal section, there is no change in mass, so 0 mass change, but there's an actual increase in the atomic number. For that to happen, we must have the emission of a beta particle. So a beta particle is what is emitted where we have a change here from lead to bismuth. So as we go down, we can identify the sections where the beta emitters are and where the alpha emitters are. And it's probably important for you to have a bit of a look in a little bit more detail, which we'll do in class, at this particular sequence, because there are some accompanying alpha radiation emissions that accompany some of these steps. But in a very general sense, you just have a look at the alpha particles, which are dropping mass and atomic number down with 2 protons and neutrons, and the beta particles, which are not changing the mass of the atom, but are changing its atomic number. Thanks for listening.